Okay, it seems we're live. Welcome back. So today I've got quite a lot of things to show you. I haven't been doing one of these in a few weeks, so there's quite a few things that has happened. A lot of parts have arrived, also a few boxes that I need to unbox for you, and overall there's a lot of things that I need to show you. One thing I managed to do over the past few days and weeks was to remove all of the drives and all the electrical equipment out of the boxes. Reason being, I'm very constrained in space, so I had to get rid of most of the boxes, and I didn't want to just leave the components lying around, so I decided to mount them in the control cabinet. So I ended up buying the control cabinet. I wasn't planning to do it at this point in time, but then I did it anyway. Took me a couple of days to sort it, mount it, and put it on the machine structure. So now that's sorted, I will show you that. Then there's quite a lot of parts that have arrived, as in machine component parts. I have also mounted one of the X-axis linear rails to the granite base, and then managed to test that in a few directions. So that's seems to be very good and quite accurate. I will show you that later as well. What else? Bought some inspection tools. So a lab grade granite surface plate, plus a sort of a granite square with less than 2 micron perpendicularity. Then a few bits and bobs, and a new caliper, and a few other things. Some mechanical parts, I've sent them for modification because they had some issues with the surface finish and the flatness of one of the parts that came from China. So I outsourced most of the part manufacturing to 2 companies in China. One of them, quality wasn't that good. It was cheaper, but quality wasn't very good. So I sent them the less critical parts to be machined, and then on the other one, the quality is exceptional. It's very, very good. I've got some parts of them to show you as well. So yeah, those parts have arrived. As I said, some of them have been sent for modification, and then the rest is well, we just play it by ear. I will firstly show you the control cabinet, what we've got in there, just to explain a little bit about how the electronics work for the project. So I guess we should start from there. Right, let me bring you guys over there. Cool. So, sorry for the shaky camera, obviously I'm holding it with my hand. So this is where the electrical cabinet goes. So on the back of the machine, the width is 600 millimeters, which is exactly the same as the width of the actual machine, or the largest granite piece, which is the bed. I will show you that later, what I have done with that one as well. So this is where the electrical cabinet goes. Inside we've got quite a few components. It's a very compact scenario because obviously, as you can see, it's quite a limited space that I have here. So it's 600 mil by 600 mil, and then 300 mil depth. Let me just unlock this. Right. So that's what we've got in there. I probably should think about putting a light in there as well. So up top we've got the servo drives.
So in this scenario, for this project, I've got servo drives from two different brands. I will explain why I did that. So these are the Beckhoff drives. The first one is a power module. So this is only a power supply, and plus an EtherCAT hub, if you want to call it. So the EtherCAT connection goes in there, and then it distributes between the other drives. These drives each can control two CNC axes, so two axes basically. One will be for the X and Y, the other one would be for the Z axis and for the spindle, because obviously the spindle is also an axis because it's closed loop. So them two are for two of my axes. Then we've got those two beefy ones. Those are for the rotary axes. Beckhoff doesn't produce a drive or a servo motor as in a torque motor, like a direct drive. They produce linear motors, but they don't do direct drive torque motors. So I bought these, I sourced them from a company called CPC in Taiwan. I've used them in the past. They've got good quality components. Then on the bottom, we've got the Beckhoff IPC. So this is the brains of the operation, the controller, which is, I think it's a Core i5 CPU plus an 8 gigs of RAM and a few industrial stuff. Then I've got two identical 10 amps 24 volts DC power supplies. Then over there I've got the Beckhoff I/O board. One of them is a stepping motor drive, which is that one in the middle, which is quite interesting because the width is less than my finger. It's probably the same width as my pinky. And then a few I/Os and some temperature control I/Os. Then I've got quite a few relays, these slim relays, which will go there. And then underneath I've got like circuit breakers, quite a few of them for different drives. Then I will mount them down there. So that's the scenario that we've got with the control cabinet. Then the cables through these ductings, they come from here, they come out, they go into an energy chain and then gets distributed in various places in the machine. So that's the control cabinet situation. Then I've got the X-axis linear system. So let me just put this to the side. Well, I probably don't need it actually. I can just close this off. Okay. So what do we have here? So this granite bed, okay, the top surface is lapped, and also these two sides. So that side and that side. They are basically 90 degree to the top face. Better than 2 micron, I was told. So this is how we mount the X-axis linear rails. If you've watched the previous episodes, I think I explained how these rails work. So they are essentially creating a very large linear rail, just a one piece linear rail. The reason I use these is because you can adjust the preload of the block with these. Them two granite parallels are identical in terms of thickness, and also the sides have been lapped in a square shape to the top face and the bottom face. Okay, so the thickness of them two are exactly the same. Well, when I say exactly the same, they've been lapped together in one direction, so they should be pretty much similar. And then these faces are also perpendicular. Okay, so why did we do that? In order to get one of these rails, which is facing this way,
parallel to the back of the granite, I have machined and ground this piece. So this is a piece of stainless steel. I went for stainless because I didn't want to paint anything, didn't want to deal with rusting issues and things like that. Hence these are all stainless, even the rails are stainless. So this is stainless. You can see it's got a very good mirror finish. And it's been ground on both sides. The rear side wasn't really that necessary, but I did it anyway. So this one now is in exactly, well, it's parallel to this face, the back side, and then it comes up. So we've got one essentially just one face. It's like an extension of this face of the granite, comes up, and then this will attach to the granite. So basically, I'm now making this face and this face completely parallel. Then on this side, I've got the same scenario. So I've got another ground piece of stainless, which would be the reference for the linear rail. This will sit against that, and based on what I've all explained, now I can say that this back face is perpendicular to this back face of the granite. So the rail and the granite are now in parallel, if that makes sense. I think I once said perpendicular by mistake, but yeah, what I mean is now this back face of the rail and this back face of the granite are in parallel. Okay, so that's the reason we've played with all of these parts. There's also another reason why we've got this back plate, and that is when you're applying preload to the blocks, you're squeezing these two together. By squeezing these two together, you can't just rely on the bolts. So you have to have something like a stop, like this, to hold the rail in place. So then bolts are going through this granite and then are bolted to this piece. So I've got 4 of these holding this piece and the granite together. So the granite is basically like sandwiched between them two. So I'm just like squeezing it like that. And then we've got these bolts that hold the granite to the bed, to the granite parallel to the bed. There was quite a few tricks when I was trying to mount these. It wasn't easy, but we did it in the end. Then we've got the other one. Now, the other one, to mount this one, this is a tricky job. This is probably one of the trickiest parts of this whole assembly process. Reason being, I don't have a reference for this one. So, even though this face is lapped, I didn't want to trust to mount this against that one and hope for the best, because then if these two rails are not completely parallel down this track, on one side I will get the blocks quite preloaded, and on the other side they get a bit loose. So that's not something that we want. What we want is to have these two as parallel as possible. Okay? So how do we do that? So basically this one is fixed now, and the reference is the backside of the granite. And you usually don't want to have two references. You usually have just one datum face. The other one, you adjust it and you mount it based on the other datum. You can't have two datums. So this will be sitting almost somewhere around here, okay? More or less. So if this sits here, right, then I have to get these two parallel to each other. So how would I do that? I would, as I said, this face and this face are lapped. So we can assume by mounting these two plates, the rails are basically, the back side of the rail is here, okay? So if we can assume that, all we need to do is to make these two granite pieces
parallel to each other. One is fixed, easy. How do we make the other one parallel? Well, for doing that, or the way to do it is basically by using a DTI. So I will bring these two into relatively parallel position by just like using a caliper and a few manual measurements. Then I will bolt these, but not super tight. I'll just bolt them loosely. Then I will bring my DTI. I've got a 1 micron increment DTI. So then I'll make these two completely parallel to each other. Then I will tighten them bolts. Okay. Now you might ask, okay, so you would do that, but then you said that you want to squeeze these two together with the blocks. So if you're squeezing them two parts together with the blocks, how can you ensure that this doesn't move? So the way to do it is I've got another piece of like a strip of metal, like similar to this one, that I will bolt it here and then I will pin it to the granite. Right? So by pinning it, this ensures that it doesn't move. I'm using one of those spring type pins, so once you pin it down, it's not moving anywhere. The only problem that we have is you only get one shot. Why? Because you have to make these two parallel. You measure it like 50 times to make sure that it's parallel. Then you will bolt that piece, the strip there. You measure it again. You measure it like 50 times, literally. And once you're happy, you bolt it down. You pin it down. Once you've pinned it, you can't do anything about it, because if you've made a mistake, then that's it. So that's a little bit tricky. And this is the trickiest part of the assembly, I would say, of the granite sides. Obviously, we've got loads more going on when it comes to the 4th and 5th axis, but for the granites, this is a bit tricky. When we come to the other granite, this is already perpendicular lapped and assembled together. This is very, very accurate. So all I need to do is just to accurately mount them rails. So this should be a lot less tricky. But this one, yeah, this is quite a challenge, I would say. Right, so that's where we are with mounting the granites. I showed you that one as well. What else do we want to see? Right, okay. Now we want to see, I can show you all the measuring equipment that I've got here. Let me bring my tripod. Just hold on a second. Do you know what? I've got a part here that I can show you beforehand. Let me just bring that up. Okay. So, as I said, there's probably around, well, I can tell you, these are all the parts that came from China, all the machine parts. 34 pieces came from the second company, which was the better quality company. So 34 different types of parts have come. I've got one of them that I would like to show you. The rest are in one of those boxes, pallets down there. Right. So this is the table. So this machine's got a fixed 3-axis table plus a 5th axis table. The reason I went for a fixed table like this was because if you're doing a lot of 3-axis work, you don't want to put pressure and load on the bearings of the A and Z axis. Why would you want to do that when you can have like something as hefty as this? Again, stainless steel. They've done a cracking job of welding these two pieces together, well, welding 3 pieces together. So I've got this stiffener in the middle, and then this back face has been round in relative to the top face. Obviously, I can't trust their grinding. I think the test report that they sent me for this piece is around the perpendicularity is around 15 microns, which is a good
result for something like this big and hefty, but once we've mounted it on the machine, this is quite heavy, that's why I'm struggling. Once we've mounted on the machine to the best way, as best as we can, then I will grind with the spindle itself. I will grind like 10 microns, 20 microns off of this top face, and then that should give us a complete flat surface. So that's the machine table. You've got T-slots. These 4 holes are for a chuck that is on the C-axis. I thought maybe we would like to put it in here as well. And these 2 little holes, I don't know if you can see them, but underneath these 2 holes are for a laser tool length probe from Renishaw. So that will sit there. And yeah, that's about it really. Very, very nice machining. I mean, this is really quality stuff. So yeah, I'm very happy with this. It's all machine ground and looks very good. Right. Now let's get to the measurement stuff. Okay, let me just bring my tripod here. As you know, it's live and it can be a bit shaky, so sorry about this. Okay. Just give me 2 seconds. Right. So what do we have in here? I can actually probably sit down. Right. So what do we have here? Well, this is just a gauge pin, 12mm gauge pin, nothing fancy. This again, nothing fancy, it's just a 300mm caliper from Insize. Couldn't afford a Mitutoyo, they're a bit expensive these days. This one is, so this is a granite square, again from Insize. This is better than 2 micron squareness between these 2 faces. So that's pretty cool. What I will be using this for is, for example, if I want to measure the squareness of 2 faces of various parts, I can use this in conjunction with the granite base. Right. That's the granite square. Nice box and everything. I mean, this was expensive. This is nearly 500 quid, so this is quite expensive stuff for such a small piece. And this is a lab grade, so grade 00 granite surface plate. And this is the inspection report that came with it. It was flat to 0.6 micron. It's pretty good. Obviously, this is not a temperature controlled room, so it doesn't really matter how well. It does matter to some extent, but yeah, this is as best as we can get. Temperature here is, well, it's stable, and all of the parts that I want to measure are in this room. So relative temperature is consistent and stable for now. But then as soon as we get closer to lunchtime, then it's going to heat up, and probably the metal parts would heat up quicker than this big hefty piece of granite. But for now, it's pretty good, and it does the job that I want to. Shall I give you a couple of small demonstrations of what I will be using these two for? So let's see. Let me just clean my table. I'm just using alcohol. Now, when you clean the table with alcohol, or with any other liquid, you're cooling down the face of this. And when you do that, one thing that would happen is the surface, well, this is what I've read, I'm not sure, I haven't tried it myself, but the surface gets a little bit distorted and it needs some time to get back to the normal condition. But for the purposes of this demonstration, I think this would suffice, and we're not really too much picky about it. Okay, so let's let me bring the machine's Z-axis, and let me see if I can get this to zoom in. I should be able to. Not flip camera, but actually flip camera. There we go. Okay. So this is the machine's Z-axis, okay? Again, another piece of granite. I will clean this up as well. These are microfiber cloths, and they usually don't leave any particles on the piece. Right, okay. It's actually quite cool. When you place this in here, it creates an air bearing effect. So this is like really smoothly moving, and it's very hard to separate them. There's an air cushion basically in between them two, and then yeah. Right. Okay, doke. So this is my DTI from Marv. This is, let me see if you can see it. Yeah. So this has 1 micron increments. It's pretty accurate stuff. This is the best one that they do. I think there is a digital version which has got the same accuracy, but the resolution is higher. But in the mechanical realm, this is the best one that they do. I'll just mount this like so. The issue that I have with this is it's got very little travel. It's like 0.14 millimeter, as in 0.07 millimeter on each direction, which is nothing really. So it's really hard to control it. You need definitely to have a fine adjust on your DTI base. So I've got a fine tune on this one, which is good. This is always a bit finicky. So what I want to check now is to check for the parallelism of these two. Okay. So I want to check the flatness basically of the z-axis. And bear in mind that this is, in the worst case, it's got 0.6 micron flatness. Okay, so we go in, I can just apply using the fine tune. You can see it's very sensitive. I mean, I'm just touching this and it just goes round and round. Let's bring it to some number. I'm putting some pressure on this, so I'm making sure that it's not. Just put it a little bit more. Okay, that should be. So I'll try to zero this, but this is, as I said, this very sensitive stuff. It's not easy always to zero it down. Well, I'm just pressing on the base, so I'm making sure that it's fixed. It's 1 micron increments. It's very sensitive, so I'll avoid playing with it. So it's now reading at 14.5. So I will just move this around. Right, wait a second. I think this was stuck on that air cushion. Let's see. Right, so now this is exactly on 35, right? So let's see. I've got half a micron, I don't know if you can see it. I've got half a micron of play. One micron, half a micron. Just doing a 180. 1 micron. Half a micron. Half a micron. It's barely moving, which is a good sign. When I'm coming from this angle, it's only in this area that it drops by 1.5, 2 microns. 1.5. But all the sides, it's better than 0.5 micron. 1 micron, yeah. I would say this is it's only in the center that it's a little bit like concave like that. Only the center part. It's a little bit, yeah. But the sides where my blocks, the Z-axis blocks sit, they are pretty good. Better than 0.5 micron tolerance. That's pretty good. Right? So that's your Z-axis. I can't really. That's your Z-axis. Now I would like to do the same for the X and Y axis. That's something that I haven't done myself. So I'll do that as well. That's obviously a much bigger plate. Let me just do a little bit of cleaning again in here. Bring the other one. You know what? I would like to move this rather than the DTI. Yeah, because I'm not really sure how flat the bottom of that DTI base is. I would like to have that stationary and then move this around. So this is essentially the X-axis. That moves up and down a track. So this can... If I move it to the center here, I should be able to move this backwards and forwards. If I say that's the center. Right, so I'll just apply okay. So I'm reading 52 microns. 54 microns.
half a micron.
Yeah, half a micron from this end to this end. Now let's rotate. This is going to be a bit tricky. Just move this back. Right. Got 46 here. Again, I would say half a micron. It's very hard to define it, really. Let's see from this angle now. So I'm reading 53, 54. The reason that this changes, well, in an ideal world, it shouldn't change when you bringing it from there to there. But because the bottom face of this piece is not super flat, as you can see, if I apply some pressure, the DTI moves. So that's why I'm trying to keep this as stationary as possible. So now it's on 50 and a half. So that's 50, that's half a micron there. Yeah, half a micron. So this is pretty flat. If I bring this up and then point it like that, I probably should be able to do a reading from the middle, but I'm not really bothered about the middle because this is where the blocks will sit. So when I did it on that side and that side, I think that's pretty much what we need to know. But yeah, this is not reliable if you move this part. So you have to hold this stationary, which is actually going to be a problem, I think, when I'm going to measure the two granite parallels for the x-axis. Because if this wobbles, which it does, as you can see, unless there are two pins, let me just see if I can. No, it shouldn't be. Let me see if I can tighten this up as much as I can and see if that changes anything. Well, this is on a spring. If I hold it from these two pins on the back side and move it, then it won't change. But then if I hold this like in a cross, then it rocks backwards and forwards, as you can see. I'm not sure if you can see the little hand, but yeah. When I apply pressure like this has almost 10 microns of play. Probably the other way around as well. Well, a bit less on that side. Probably about 2 microns, but then on this side, it's definitely a lot. If I hold it from the bottom, it doesn't rock at all. So what I'll probably do is I'm just going to hold it from there and do my measurements like this. I probably should lap this at some point. Yeah, this is pretty good. Yeah, okay. I know how to read it now. So I'll just hold it from where these 2 pins are. If I hold it like that and move it, then nothing changes. Cool. So, we're happy with this. I would like to also show you the, I've received a package from Renishaw, so I'd like to show you the package as well that came from Renishaw. I'll just put this to the side and then I'll bring that package. Right. Oh, this is air vacuum now. Oh. I love it when this happens. Where's the Z-axis? Okay, I'll just clean my hands a bit with alcohol. Now I haven't seen this package, I've seen the package, but I haven't opened the package myself. So we will be doing this together. I probably can zoom out now. Back camera. There we go. So bear with me one sec. If you remember, I explained that this machine will have a closed loop system. So the closed loop system means that it will have linear encoders and rotary encoders so that we can see where the actual position of the machine is, rather than relying on the results that we're seeing from the servomotor encoders, which isn't always representative of the actual position of the machine. So for that reason, I reached out to Renishaw, and they provided this system for me. So there's 3 linear encoders in this. The rotary axis, they've got their own encoders, and they are directly mounted on the shaft that rotates. So basically I don't need a second encoder for the rotary axis, because it's a direct drive motor. If you're using a gearbox in the middle, then you would definitely need it. But if you're not using a gearbox and it's a direct drive, directly mounted to the, as the robotics people call it, end effector, which is the final piece that moves, then you don't need obviously a second encoder. So that's the scenario for my case. I'm just cutting this open. These are tough tapes, Renishaw people. got it open finally. It's got loads of these paddings. So the linear scales, they've got a resolution of 50 nanometers. I could have gone for something around like even as small as 1 nanometer. The reason I didn't do that was because that will increase the amount of data that is sent to the amount of data that is sent to the servo drive, and it's just increasing the it's using more capacity of the network, the EtherCAT network. So there is not a huge reason for doing that, because I'm trying to get a repeatability of around plus minus 1 micron out of the machine. So if that's the result, if that's the case, then 50 nanometers is 20 times smaller than that. So it should be sufficient. So this is the package of one of these linear scales. It's pretty lightweight. So 50 nanometer scale. This is the longest piece, 500 millimeters, which is for the longest axis, as you can imagine. Just got to be careful with this. Clever packaging. It's placed in between these two portions of the cardboard box. I'll just slide it out. It's in a plastic sheath, so obviously I'm not going to remove it. So this is the scale with 50 nanometer resolution. This is already mounted on a piece of, they call it a spar or stainless. I'm not sure which one this exact one is. We've got the Renishaw logo there, made in UK, and yeah, very quality stuff, as you would expect from any Renishaw product. So it's very accurate stuff, very quality. Let's see if this is the, oh yeah, okay, so this is the calibration certification. Each of them, they come with a certification like this. So this is your error in microns for this length. The accuracy specification is plus minus 1 micron for this length. As I said, the resolution is 50 nanometers, but the accuracy is plus minus 1 micron. Now the results of this particular encoder that I'm holding in my hands is plus minus 0.19 microns. So that's in the length of this, of the whole like half a meter. This has got less than half a micron of positional accuracy error. That's really good. Really, really good. Less than half a micron. So based on this, I should be able to position the x-axis better than half a micron in a 400 millimeter span, which is the x-axis stroke for my machine. So that's pretty good. Yeah. I don't know if this is just a coincidence or not. The serial number is 5MHR76. Now usually when people want to shorten my surname, they put it MHR. So, coincidence? It's interesting. Alright, this goes in there. So I'm not going to open the other two, but as you can imagine, they are pretty much the same, just a bit shorter. This was good. Like this. There's two more. Yeah.
2 more, and then there's the reed heads. So I'm gonna open one of them reed heads as well.
So this is one of the reed heads. Well, I think. So as you know, a linear scale, if you know how it works, you've got a stationary, like a tape, which is your scale, and then you've got a reed head, like a sensor, that reads that. And it comes with its own cable, like this. And that's your reed head. Should I remove this? Yeah. So this is optical absolute encoder. So it's not incremental, it knows where it is, the position. Hence I don't have any homing sensor for this machine. So that's your reed head. It's from their Resolute series of encoders. And that's your, if I can put my hand behind it, so I hope it focuses. And that's the optical sensor that reads those little lines that you saw on the tape, on the encoder. Yeah, very cool. Just carefully put it back. I don't want to contaminate it or damage it. So that's one of the reed heads. I've got 3 of these, obviously, for X, Y, and Z. Then the last thing in this box is one of their diagnostics tools. Can't remember what they call it, ADT or ADTA. Yeah. So this is just a little device that you connect to your encoder. This is just for setup, just to monitor the quality of the signal that you're getting, if the encoder is feeling okay, if it's reading correctly, and you can connect it to a software, I believe, to your computer to see the results of this, that are coming back. So this is, well, I mean, Renishaw stuff, they are really good, really quality stuff. This is anodized aluminium, the body. I was expecting this would be plastic, but no. So you've got your signal strength level there. I haven't read the manual really yet. That's a USB. They need to update these. This is this is mini USB. Well, they've gone extinct now. Yeah, this needs to be USB Type C, hopefully, at some point. Then on this side, you've got your encoder input, and then that's how you read it. So that's pretty cool. A little device to make sure that everything is okay. But as I said, you don't need this when the machine is working. This is just for setup. It goes in there. Okie doke. I've showed you this as well. Nice cobalt packaging. What else is there to see? I think I've showed you most of it. I've showed you the control cabinet, the X-axis, these parts. I don't think there's anything more really to see. I think this is a good 1 hour summary of what's been happening. Let me just put you back up there. This is the main camera, isn't it? Yeah. So yeah, that was it. So thanks for tuning in. If you haven't subscribed to the channel, please do hit the notification icon, because I will be randomly going live, and then you can jump online and watch the video when I'm here and actually doing it and talking about it. If you've got any questions, please put them in the chat box, even if this is after the live session, or you can just comment it. I think the live chat box will close actually, but then you can put some comments in if you've got any questions, and then I will explain it to you, or I'll try to clarify. And yeah, thanks for coming in, and I'll see you in the next one. Cheers, bye.